Okay. So, we have derived that all pole model for vocal tract. So, Vz is nothing but a, I can say the G by dz. Okay. So, where dz is nothing but a 1 plus k, sorry, summation of k equal to 1 to n alpha k z to the power minus k. Okay. Now, if you see the the second for the 2 tube model, the equation Vz is nothing but a 0.5 1 plus Rg 1 plus R1. So, for 2 tube model Vz is n equal to 2, n equal to 2 is 2 tube model 0.5 1 plus Rg 1 plus R1 1 plus R2 into z to the power minus 1 divided by, I can say 1 plus R1 R2 R1 R2 R1 Rg into z to the power minus 1 plus R2 Rg z to the power minus 2. So, dz for 2 tube model is nothing but a 1 plus R1 R2 plus R1 Rg z to the power minus 1 plus R2 Rg z to the power minus 2. Now, if I say Rg is equal to 1, if I say Rg is equal to 1, total impedance is infinite, Zg is equal to infinite, then Rg equal to 1. So, Rg is nothing but a, you know that Rg is Rt minus Rg divided by Rt plus Rg, or what was Rg minus Rt or Rt minus Rg, Rg minus Rt. So, that is there in constant when we model in that boundary condition, when we model in boundary condition we said Rg boundary condition modeling where here. So, here I can say Rg is nothing but a Zg minus Zd divided by Zg plus. So, Rg is nothing but a, here I write capital Rg, let us consider small rg, Rg is Zg minus Zd divided by Zg plus Zd. If Zg is infinite, then Rg is equal to 1. Okay. Now, if I consider Rg is equal to 1, then dz is nothing but a 1 plus R1 R2 plus R1 z to the power minus 1 plus R2 z to the power minus 2. Okay. So, if it is nth order, if I can write that if it is instead of 2 tube it is n tube, or I can say it is nothing but a 1 plus R1 R2 R1 z to the power minus 1 plus R2 z to the power minus 2. Okay. So, if I say that okay, I can want to write down the recursive equation. So, d1z, if it is d2z, so d1z, if I write d1z is nothing but a 1 plus R1 z to the power minus 1. If Rg is equal to 1, d2z is 1 plus R1 z to the power minus 1 plus R1 R2 z to the power minus 1 plus R2 z to the power minus 2, that I have derived here, z to the power minus 2. Now, if I say this is nothing but a d1z 1 plus R1 z to the power minus 1 is nothing but a d1z. Okay. So, d1z plus R2 z to the power minus 2 into d1 z to the power minus 1. R1 R2 z to the power minus 1 plus R2 z to the power minus 2, this term can be written like this way, R2 z to the power minus 2 into d1 z to the power minus 1, because d1 z to the power minus 1 will be 1 plus R1 z to the minus 1 instead of z. So, z. So, R1 z into this one. So, R1 R2 z to the power minus 1 and R1 z. Okay. So, this can be also written like d0 z, there is no junction, no nothing is there, is 1. So, it is nothing but a d0 z into plus R1, I can say z to the power minus 1 d0 z to the power minus 1. Okay. Similarly, I can write down this way, because this is nothing but a d1, we put d1 value and this will come same value in here. Okay. Similarly, I can write dnz or dkz, dnz, I can write nth tube, n number of tube. This is nothing but a dn minus 1z plus r2 z to the power minus n dn minus 1 z to the power minus 1. Or I can say dkz is nothing but a dk minus 1 z plus r2 z to the power minus 1 dk minus 1 z to the power minus 1, which is same as if I write the equation dz is equal to 1 plus k equal to 1 to n alpha k z to the power minus k. Same way I can write. So, this can be written as like this way. Okay. So, if I write this one, if n is equal, number of section is equal to 10 and let us Rn is equal to 1, load what Rn is equal to RL. So, let us load is RL is equal to 1. Okay. So, no resistive load for low frequency Rn is equal to RL, which is equal to 1. Okay. Now, I can say I can find out the what is the value of, if I know that Rn is equal to 1, then from that side last side this last Rn is equal to 1. So, I can find out Rn minus 1, Rn minus 2, Rn minus 3, if it is 10 tube model. So, Rn means R10 is equal to 1. I can find out R9, R8, R7. How? Because using n equal to reasonable number of tube, then model Rn equal to 1, Rn equal to, let us this one n plus 1 is equal to 18 centimeter. So, what is saying that if I know the reflection coefficient, I can implement the tube, digitally implement the tube. Or other hand, if I know the signal which is coming out from the tube, from there I can estimate the area function of different junction. Because if I know Rn is nothing but a, what is Rk? Rk is nothing but a k plus 1 minus a k divided by a k plus 1 plus a k. So, a k, a are the area cross sectional area function of the tube, different tube. So, if it is a 10 number of tube consist of the vocal tract is modeled using a 10 number of tube, last Rn is equal to 1, last one is equal to 1, then I can find out a k. So, Rn I know Rn, so this is Rk. So, I know Rn is equal to a n plus 1 minus a n divided by a n plus 1 plus a n. So, if I know the cross sectional area, then I can know the derive the reflection coefficient and I can model the tube in digital domain. On the other hand, if I know the speech signal and if I able to find out the value of reflection coefficient alpha k, in somehow I can able to find out the alpha k value, then I can find out the cross sectional area of the different tube. I can give you one example from Rabin and Shepard that is written, there is a different cross sectional area for a vowel. I think the vowel, which vowel I do not know, that there is a vowel. So, this vowel area functions is written. Either I know the area function, I can generate the vowel. If I know the vowel, I can derive the area function. Okay. So, how do I digitally implement this tube? I want to digitally implement this tube. So, I know I have to implement dz is nothing but a 1 plus k equal to 1 to n alpha k z to the power minus k. This equation I have to implement. So, if I am able to implement, how do I implement? Very simple. So, there is a UN, let us n UN n impulse, then I have a output which is ULN. Okay. So, this will be simple delay by z to the power minus 1 alpha 1 and has to be added with here, then z to the power minus 2 alpha 2 added in here dot 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 z to the power minus n alpha n added here, this is 1. Okay. So, I can implement in digital systems, I can implement it digital filter, nothing but a digital filter, the equation looks like a nothing but a digital filter. So, I can easily implement it using that things, that vocal track I can implement using digital domain. Okay. So, now there is some concept, poles of vocal tract. So, you know that poles, all pole models of vocal tract tube. So, I can say the VZ is model using G by dz, where dz is equal to 1 plus k equal to 1 to n alpha k z to the power minus k. Okay. So, dz has an n, if it is order is n, so n number of pole. So, I can say VZ is a all pole model which has n number of pole. So, if I have a 10 junction tube, 10 section tube, then I can say 10 poles will be there, 10 poles will be there. So, now if dz is real, so the dz have either the all real pole will be the real function. So, there will be real pole will be occur, or there will all pole have a complex conjugate in nature. So, if dz has a n number of pole, then I can say there is a n by 2 complex conjugate pole will be there, n by 2 pair of complex conjugate pole. So, I can say Vz is nothing but a G by k equal to 1 to n by 2 1 minus alpha k z to the power minus 1 into 1 minus alpha k star z to the power minus 1. So, it is nothing but a n by 2 complex conjugate pole product. Okay. So, what is if you see that, then if I say this is my unit circle. Okay. So, complex conjugate pole. So, this is the real axis, this is the imaginary axis. If a pole occur in here with the angle of theta, there will be another pole which is conjugate this pole minus theta in here. So, if there is a pole in here, there will be another pole will be in here. If the pole in here, there will be another pole will be here. So, every pole has a complex conjugate pole. Okay. If it is complex number, then alpha k I can say it is nothing but a r k e to the power j theta. So, a complex number has a pole, this is the pole. So, this has a theta and this has a amplitude r. So, alpha k can be represented using r k and e to the power j theta. This r k is not reflection coefficient. Okay. So, there is a amplitude of the pole and e to the power j theta. So, if I say alpha k complex conjugate part, it will be nothing but a r k, amplitude will be same, e to the power minus j theta. Value of alpha, complex conjugate pole. Okay. Now, interpret the value of alpha. So, if I do that, if I put the value of alpha in here, then the dz will become, or you can say Vz will become G by 1 minus alpha k z to the power minus 1 into 1 minus alpha k star z to the power minus 1. Let us this write down this product, I have not, and product of k equal to 1 to n by 2. So, if I do this one, instead of alpha k I put the value of r k e to the power j theta, instead of alpha star k I can put the r k e to the power minus j theta. If I put that value, it will come G by 1 minus 2 r k cos theta k z to the power minus 1 plus r k square z to the power minus 2 for this complex conjugate product. Okay. So, I can now if you see the Vkz in term of this one, this is Vkz. Vz, if I want Vz, write Vz, then there will be a product of pi equal to k equal to 1 to n. So, Vk I can say this 2 only. This is if I write Vk this one, then I do not write this product term. Okay. Now, if it is that, then what is contribution of Rk and Bk? Let us Rk is equal to e to the power minus Bk and Bk is equal, so Bk is equal to minus ln Rk. Okay. If I put that value, then Vkz will become 1 by 1 minus 2 Rk. So, 2 e to the power minus Bk cos theta k z to the power minus 1 plus e to the power minus 2 Bk r square k. So, z to the power minus 2. Now, importance of this Bk is nothing but a produce a bandwidth. Bk produce a bandwidth and theta k give the formant position. When the value of Rk approach to unit, I can get the formant frequency, resonance frequency. So, if it is Rk approach to unit circle, close to unit circle, then I can get the resonant frequency. And if the Bk value is non-zero, then I get a bandwidth pole. There will be a pole, there will be a formant which has a bandwidth. Okay. So, Bk provide me the bandwidth, theta k provide me the formant position. So, this information will be used when we develop the model using linear prediction model for speech production system. Okay. So, if I know the theta k, and value of Rk, then I can model the system. Theta k give me the formant frequency position, and if Rk tends to 0, tends to unit circle, amplitude of that pole is tends to or close to unit circle, that give you the formant frequency. Okay. So, if there is a n number of pole, so n by 2 complex conjugate pole will be there. So, each pair of complex conjugate pole give me a formant frequency. So, if I have a 5 formant frequency, if I give you a spectrogram or let the I told you the spectrum of the speech signal is like this 1, 2, 3, 4. Let us F1, F2, F3, F4. Then if I ask how many complex conjugate pole will be there? 4 pair. How many pole will be there? Complex pole will be 8. So, if n tube model is there, n number of pole is there in a transfer function, then I can say n by 2 complex conjugate pole will be there. So, literally I can get n by 2 formant frequency in the spectrogram. Okay. So, if I give you the formant frequency and formant bandwidth, if I able to find out for a speech event, I can able to derive the transfer function for that speech event, the vocal tract transfer function. Now, if I say that event is given, so speech event, let us say speech event, the steady state vowel a. If I take the steady state vowel and analyze the frequency analysis and find out the formant frequency and formant bandwidth, then I can able to find out the transfer function of that vocal tract. Okay. So, complex conjugate now, so do not confuse with number of complex conjugate pole and pole, number of normal pole. Okay. So, if there is a n tube model, n tube model is there, then I can get n by 2 complex conjugate pole. So, there will be a n by 2 Formant. So, if I able to, let us there is a n equal to 10 tube, I take 10 tube to model this, this whole vocal tract system is divided by 10 parts and model it, then I can get 10 by 2 complex conjugate pole. So, I can get 5 Formant frequency. Okay. On the other hand, let us derive that mathematics. There is an example I have given in the slides. Let us the length of the vocal tract L is equal to 17 centimeter and the velocity of sound is 340 meter per second. Find the number of sections required to generate 5 kilohertz bandwidth voice signal. So, I have to generate 5 kilohertz bandwidth voice signal. What should be the sampling frequency? Fs should be 10 kilohertz, okay or not? Fs should be 10 kilohertz. Then what is my tau? Tau is nothing but a x by c. So, what is x? X is the length of each section. Okay. I have to find out number of sections required. So, let us I require a n number of section. So, if the length of the tube is L, then the x is equal to L by n. Okay. So, then tau is equal to L by n into c. Okay. Now, if it is L is equal to 17.5 centimeter and c is equal to 35 centimeter per second, then I can find out it is nothing but a 17.5 divided by n into 35300, which is nothing but a 175 divided by n into 350, let us write 350 into 10 to the power 3. So, it is 2. So, it is nothing but a 1 by 2 n into 10 to the power 3. Okay. Now, what is tau? So, what is t? T is equal to 1 by Fs. So, that t is nothing but a t is equal to 2 tau. So, tau is equal to t by 2. Tau is equal to t by 2. What is t? T is nothing but a 1 by Fs. So, it is nothing but a 2 by Fs. So, I can write 1 by 2 Fs is equal to 1 by 2 n 10 to the power 3, 2 to cancel. So, it is n is equal to Fs by 10 to the power 3. So, Fs is equal to 10 kilohertz, which is 10 kilohertz, nothing but a 10 section. Okay. Or I can say n is nothing but a Fs by n by 2, I can say n by 2 is nothing but a bandwidth, if it is Fs is equal to 2b 5 kilohertz. Okay. So, 10 section is required to model that tube, 5 kilohertz bandwidth, I require 10 section. So, similar kind of mathematics you can expect that okay, if I want to generate 4 kilohertz bandwidth signal and Fs is equal to let us 8 kilohertz, sampling frequency is 8 kilohertz, then find out the number of section is required, minimum number of section is required. Okay. So, I can find out the number of section is required. So, this way I can find out and this way I can model that signal. So, since that vocal tract can be modeled as a all pole model, I am not going details of that things, this is the Formant trajectory. So, I can see that whole Vz can be, so this is the Vk is the product of this, if it is right Vz, then product will be here. So, I can say this digital implementation again same, each of the chunk represent the Formant frequency. This is the first Formant 1, Formant 2, Formant 3. So, that will come. So, each stage represent one Formant frequency. Each stage represent one Formant frequency. So, there will be n by 2 number of stage will be there. So, if it is n by 2 number of stage, then n by 2 Formant frequency will be there. So, I can say that lossless tube model, lossless vocal tube model can be done by a linear system, which is nothing but a VZ is a linear system. VZ is equal to 1 plus k equal to 1 to n alpha k z to the power minus k LTI. So, we will discuss about that LTI system. So, this I can say in summary, this is the vocal tract VZ, radiation is RZ and glottal plus is GZ. So, if I say what is the total transfer function is nothing but a HZ whole speech production transfer function GZ VZ into RZ. Whole HZ, if I say from the speech I want to find out HZ, it is the product of glottal pulse transfer function, glottal generated glottal transfer function plus vocal tract transfer function into vocal tract transfer function into lip radiation transfer function. Okay. So, if there is a voicing impulse train will be there, that will be modified by the as per the glottal transfer function, and that modified signal fed to the vocal tract, and after lip radiation I get the speech signal. If it is unvoiced speech, then I can say it is connected to random noise and it will only modify by the vocal tract and lip radiation, and I get the speech signal. Okay. So, random noise passes through vocal tract and included lip radiation produce the speech for unvoiced speech. If it is voiced speech, impulse train will be modified by the glottal pulse generator, and that will pass through the vocal tract and lip radiation produce the speech. So, if you see 3 transfer functions, GZ can be approximated by the second order this 2 pole function. For radiation there will be one single pole is required. So, 2 plus 1 3 pole, if I do that, then I can get HZ. Okay. So, we will discuss about that how many pole, what is the order of the linear prediction analysis, that things during the linear prediction analysis function, what is the, how do you get the order of the linear prediction, that time we use this information. Okay. So, this is the whole vocal tract tube modeling. So, in summary I can say the vocal tract, this human vocal tract can be modeled using a digital signal processing, or can be implemented using a digital linear filter based on that requirement. So, we have shown that if I consider this vocal tract is a is a simulated using a number of junctions or number of section lossless tube section, let us n number of lossless tube section, that then it can be implemented using a linear system which is VZ and which can be implemented in digital domain. So, that is why this is called uniform tube modeling. Throughout the section, if I say n number of section, throughout the each section the cross sectional area of the vocal cord I said uniform. So, I can say throughout the whole vocal tract can be a single tube, whole vocal tract can be 2 tube, or whole vocal tract can be n number of tube, but if I say n number of tube, each tube cross sectional area is constant. That is why uniform and lossless also, because if it is lossy, then all kinds of complexity will come up. So, if it is lossless uniform tube model, then it can be implemented using digital system, that is VZ. Once I know that, then I know, yes, if it is implementable by a VZ, then can I think that output speech which is collected using a microphone can it be analyzed using a linear signal processing? Yes. So, that is from there the concept of linear prediction analysis comes. So, this system can be linearly modeled. So, from the signal If I want to find out the transfer function, that is why I want to predict the vocal tract constriction. So, if I know the signal, yes, it is possible to find out the area, cross sectional area of different section. If I say it is n tube model, n different section cross sectional area is possible to find out from the behavior of output speech. Or if I know the area function, I can implement it digitally. It is possible to implement it. If I excited by impulse response, I can able to produce the speech. Okay. So, this is a tube modeling. So, this is called uniform tube model or lossless tube modeling of speech production system. Okay. Thank you.